This weekend is a seminar on the philosophical foundations of quantum gravity, and we just wanted to say a few words about why philosophy kind of enters into the story at all. At least how we see it. Partly, I hope to get on the same page as philosophers and people who are engaged in this kind of inquiry already, and maybe to people who are coming from the physics community, give a sense of why this might be a valuable enterprise. Okay, well, I'm going to give the part called Nick's part, and then Chris will come and guess what? So to address this question of, how do philosophy and physics relate in a useful way, I want to go back to a historical case where we can see a little more clearly what's going on, and in particular to the development of mechanics in the 17th century. And these figures up here are three of the main figures in that story. Descartes, that's Newton's death mask, which is kind of cool, and Leibniz. These three, we think of Descartes and Leibniz maybe more as philosophers now, but all three of them were serious, scientists in the sense of the time, and all three made important contributions in the development of mechanics, classical mechanics as we know it. But interspersed in the very same books and works in which they were developing mechanics, obviously Descartes and Leibniz, all three of these were significant mathematicians. But in the very works in which they're developing mechanics, we see things that look strangely sort of philosophical, and which have sort of engaged philosophers. And in particular, I want to focus on a question they all seem to turn to: what is the nature of motion? So clearly we can think of just relative motion, pick some standard of rest and some sort of reference body and talk about motion relative to that. But part of the development of of mechanics, there was the idea that there was more to motion than just relative motion, but there was some real fact about what motion was, some privileged sense of motion. And here's what the three of them said. So Descartes, in his Principles of Philosophy, said, in accordance with the truth of the truth, motion is the transfer of one body from the vicinity of the other bodies which are in immediate contact with it. What's going on here? Descartes believed in a plenum. There's no vacuum, matter everywhere, so pick a body, it has to be completely surrounded by other matter. And his account of motion, of true motion, is something is truly moving, not when it's just in relative motion, but when it's actually basically changing the surrounding bodies. It's moving from contact with some set of bodies to some others. Like a stone dropping through a swimming pool, something like that. Newton, probably more familiar with his account of what motion was. For him, true motion was absolute motion, and to make sense of that, he postulated absolute space, seems as a kind of background, and then motion is just moving from one part of absolute space to another. Those of you who are sort of historians of this period will note that I'm glossing over an awful lot here, but that'll do for our purposes today. Leibniz, you probably know, was famously as a relationist, but in fact he didn't think relational motion was kind of real in the fundamental sense. Okay, if you actually read his works on mechanics, and indeed you can find it in the correspondence with Clarke, with the Newtonians, this is what he said true motion was. He says there's a difference between a true motion of a body and a mere change of place relative to another body. But when the immediate cause of the change is in the body, that body is truly in motion. But what did he mean by immediate cause? So he has the idea here that we can appeal to what makes something really move is if there's somehow something in it making it move. What did he actually have in mind here? Actually, what he has in mind here is kinetic energy, what we would call kinetic energy. He thinks that every body has associated with it some particular quantity mv squared corresponding to its kinetic energy. Or in other words, equivalently, everything has a speed associated with it, so numerically speaking. And this motive force is the power of it, is the cause of it moving. and something is moving just in case its kinetic energy is non-zero. All right. Well, where are these kind of, some of them sounding kind of weird views sort of coming from, and why were they unable, from our point of view, to sort of distinguish these philosophical speculations from physical ones? Well, the fact is, what they're saying here is part and parcel of their ideas in mechanics. If you want to understand, or at least a large part of why they said these things, what you need to do is look at the laws of motion that they postulated. Descartes gave a series of laws of mechanics, collision mechanics, which said in part, two of them said, imagine you have bodies of equal mass. So consider one situation where they're moving together with equal and opposite motions, in which case he said they would bounce off. This was the right answer. But he also said if they were the equal and opposite equal bodies, and one of them was at rest and the other one was moving, then they would move off together. Now, from a Galilean point of view, that doesn't make the slightest bit of sense, because these are just this, this and this are the same situation from different frames. But think about it. From Descartes' point of view, if motion is motion relative to the immediate surroundings, these can be distinguished. Is this body moving with respect to its immediate surroundings, or is it just sitting with respect to its immediate surroundings? Again, that view of what motion is ties nicely with what he thought the laws of mechanics were. Wrong, of course, but Newton, well, why did he need absolute space? Well, okay, I take it most of us, for all of us probably, the theory of gravitational theory and Newtonian mechanics makes kind of clear why we need to be able to distinguish accelerated from inertial motions, and absolute space will do that. Leibniz, well, I already mentioned, he thought you could distinguish motion from, so true motion from true rest in terms of kinetic energy. That ties in exactly with the theory of mechanics that he developed, which is basically what we would call today the theory of elastic collisions, or ironically Newtonian collision theories. Leibniz, as far as I can tell, was the first one to write these things down. If that's what your theory of mechanics is, then sure, looks like kinetic energy is a really important quantity. So this is just a very sort of short story, but the point is, the reason they were interested in these sort of, seems like philosophical arguments to do with the nature of motion, is because they were working out theories of mechanics and needed a theory, and mechanics is the theory of motion, they needed a sense of, each of them needed a sense of motion that would make sense of the laws of mechanics that they developed. Okay. I'm going a bit off. Why did this happen? Why did they end up having to involve in what we would otherwise think of as philosophy when they were doing their science? Sort of, I want to give a two-part sketch of why this might happen. So, first of all, imagine that a new science, I'm thinking about physics in particular, a new theory is being developed and it starts talking about introduces new concepts into the to us, or it significantly changes existing concepts. How are we supposed to know what those, how do we know what those concepts mean? It's a nice sort of philosophical question. And here's a sort of a standard philosophical answer. It's not the only one, but here's one way in which this happens. To understand a new concept, well, is to understand the theory in which it appears. That theory will tell you the properties of the new things, it will relate them to phenomena, to existing theories, and to understand what the concept means is to understand, in part, how it functions in that theory, and in particular, how it functions in that theory in relation to the things that you already understand, things in theories that we already have. Okay, so that's a sort of account of meaning of concepts. But now consider the sort of the historical fact that theories don't sort of just appear fully formed, a fully constructed formalism from which we might read off a concept in this way. That's not how things go. Instead, in new periods of physical revolution, we have different clues, different insights, and different theory fragments, some of which cover different areas, some of which are conflicting in certain ways. Things are done much more fragmentarily. Sorry, that's Athena coming out of Zeus's head, fully formed. The myth is she was born as an adult, fully formed, and so that's a picture of what science is not like. So put these two things together, concepts are given by their sort of place in the theory. The theory is fragmentary and conflicting. The theoretical concepts are also going to be conflicting and fragmentary, and work needs to be done thinking about those concepts. So, in short then, as a matter of fact in history, and in the little history we looked at, and I would say, given that if you buy the story I just gave you, it's not surprising this happened, part of the work of sort of unifying, what do you want to do in producing a new theory, unify the fragments into some kind of unified whole. Well, part of that work involves looking at the concept fragments and trying to figure out unified concepts. And here, I think I'm really following work that Michael Friedman has sort of done over the last decade or so along this sort of line. But that's just what philosophy of physics, a certain kind of philosophy of physics does. It's involved in looking at new theories, trying to figure out how the theoretical concepts are working in them, trying to figure out how to unify concepts across different theory fragments. And I say, Descartes, Newton, Leibniz, what they were trying to do in the works that we looked at the beginning was exactly that. It's trying to figure out how to unify the concepts as part of how to unify the theories, the formal theories that they were developing. And that's how you should think about it. Okay, well that's all very nice if I'm right about the 17th century. The question facing us though is, do we find ourselves in that situation with regards to quantum gravity? And now I'm going to invite Chris up here to convince you that we do, obviously.
Okay. Thank you. Well, I only have a very few minutes and I don't think I need much more, because you are all probably here just because you are convinced that in a way we are in quantum gravity in a similar situation as Descartes and Newton and Leibniz were in the 17th century. We are confronted with a conflicting and conflicted theory or theories, fragmentary for sure. And we don't quite know how to put all of this together into the final, true, fundamental quantum theory of gravity. And essentially it is for that reason that we do think that there's a tremendous amount of sort of philosophical, foundational, conceptual work that needs to be done in quantum gravity. So let me really try to be brief here. Just to define the subject, perhaps, what we're going to talk about when we say quantum theories of gravity are any theory which is consistent. That may be a relatively low sort of threshold, but nevertheless it's one condition, so it's a consistent theory that combines gravity with some quantum description of matter, and in that sense at least unifies the classical general relativistic description of space and time, or of gravity, with a quantum description of matter, in particular with the standard model of particle physics. Now, that's the ultimate goal, to sort of bring together quantum effects and gravitational effects. To that effect, that's a very general definition. And for that to succeed, of course, you wouldn't necessarily have to quantize the gravitational field or treat it in exactly the same way as you do matter fields. Maybe there's much more freedom available there. There are, as I think most of you know much better than I do, that there are very compelling reasons that we should, that we do need such a theory, which combines quantum effects with, essentially with strong gravitational effects. And so we need such a theory. And it turns out, if you study, as Nick and I do for our project, various approaches to quantum gravity, that in many of them, they either presuppose or entail as a consequence, in one way or another, have as a feature that space and time may be completely absent. So it's not perhaps maybe so much motion as it was for Descartes and colleagues in the 17th century that is at the center, but space and time and the reconceptualization of space and time that clearly seems to be underway when we look at many of these approaches. Not all of them, but many. And of course, whether or not there is space and time depends on how you define these things. Arguably, there's different degrees in which space and time may be absent in different approaches to quantum gravity. If you're extremely liberal at what you want to call space and time, you may still call whatever fundamental structure you have space and time, but notice in all these approaches it's going to look very different from the way relativistic spacetimes look like. And we have written up this last point in a little bit more detail in a paper that was just published as part of a special issue of studies that we edited, where some of you contributed as well. So the idea is roughly then that just as tables and chairs and things like that emerge from what fundamentally constitutes matter, whatever these fundamental constituents are, relativistic spacetimes, that's my depiction of relativistic spacetime, emerge from something fundamental, some fundamental structure which is quite radically different from relativistic spacetimes. Here, this is a causal set, but it doesn't matter what it is, whatever the fundamental structure is, radically different. And in some way, spacetime emerges out of that. And the central question is now to understand how that emergence happens. And that question, of course, will involve a lot of hard, heavy-going mathematics for which I'm not qualified, and I will happily leave that to my colleagues in mathematical physics. But I think that's not enough. That's not the only part. That will be part of that story, if we can fully articulate it. A large part of it will be foundational, conceptual, broadly philosophical considerations that will have to come into play as well. Okay, so we claim that the picture that Nick sketched in the previous part applies especially to quantum gravity, and that philosophical work on its foundations seems urgent and certainly well advised. There's at least two reasons. One is that when we think about how to give meaning to theoretical terms or concepts, quantum gravity is, of course, notoriously far removed from a direct empirical access. And that means the further removed, I think, the sort of perhaps more tenuous and longer the connection between our theoretical concepts and ordinary concepts becomes. And that means there's, of course, a place for philosophy to come in here. And secondly, space-time, whatever your day job is, if you're a physicist, in whichever theory or area of physics you work, I can almost guarantee that you presuppose some notion of space and time. Yes?
Can I manifest my ignorance immediately? What does it mean, ostension?
Yeah.
Ostending. So I can say, this is a table, this is a chair, this is, I can point to stuff and I define things in my ordinary experience. But how do you point to a causal set? So clearly giving meaning to theoretical concepts like that is not going to work. So the story of what the wave function is, or what this and that means in quantum gravity, is going to be much more involved than just pointing stuff out. And so this story will be more involved, and arguably involves essentially philosophical conceptual analysis, not just mathematical cranking of the system. Okay. Now, if space-time is not going to be part of the fundamental theory, that raises a lot of puzzling questions, some of which I will try to sketch in more detail tomorrow in my talk. Okay, so Nick and I thought this is the opportune moment for, first of all, have a special issue of studies edited to write the book together, and to have a meeting like that, which we hope will not be the last. but only the first in a series of meetings on the philosophical foundations of quantum gravity. It seems as if we're right now in quantum gravity stage with many competing insights and programs. Now, if you are working in one of these programs, you may disagree with that, with what I say here. There's no clearly emerging winning approach. You may think, oh no, of course there is, it's mine, right? All the other people in the other approaches just don't get it, or not yet anyway. Well, fair enough. I think, as participant in that research program, you're absolutely entitled to be convinced that you are, sort of betting on the right horse in the race. But I think if you remove yourself a little bit from a somewhat more neutral, a little bit more disinterested perspective, you have to say there's not clearly one emerging approach, I think, and there's a lot of open questions and a lot of conflict and debate about the most fundamental and basic principles that there are. So in such an anomalous state of the science, then there seems to be plenty of work to be done conceptually and philosophically, apart from the more formal and mathematical work, of course, that also needs to be done. All of this, before I stop, I don't mean that there's always a clean and clear separation and distinction between the mathematical and formal technical work that physicists do and the sort of philosophical work that philosophers are engaged in. That's not what we're trying to say here. As a matter of fact, there's a whole spectrum of different approaches, and they ideally sort of blend in, and many of us can contribute from different perspectives. And that's everything on the slide, but maybe before I stop, one more cautionary remark if you're a physicist, and I know that many of you are physicists, and maybe this is the first philosophy conference that you attend, just to sort of give you a little bit of a sense of what to expect. A lot of what philosophers will present, including me tomorrow, will look like physics. It will look like I'm proposing some maybe perhaps novel contribution to a new theory, when in fact this is not what I'm doing. What I'm doing is just trying to digest and represent to you the work that others have done. I don't claim any originality, and sometimes philosophers don't claim any originality as far as the physical, the development of the theory itself and its formal development is concerned, even though some of us do that too. But it's more the reflecting of the conceptual analysis of the work that physicists have done that I hope will be emerging there. So okay, did you want to add to that? Okay, so I should stop here. Thank you very much.